All right, so for the last time, I just uploaded the slides for today's material on Classroom. So if you need them, please go download them and we'll start now. So welcome to AI504 week 2, basic machine learning. So up to today, we will, only up to this week, we won't be learning any PyTorch. We'll be only learning the basic concepts. So today we'll be covering very briefly about very high level concepts of machine learning. So not all of them, because machine learning itself can be a semester, it could take a whole semester to go over only the basic concepts. And today we're going to have to cover them in 1.5 hours. So you can expect a lot of details are going to be missed. And this Thursday, we will be practicing scikit-learn. So scikit-learn is a Python library that has basically all machine learning related stuff, except for neural networks. So neural networks, we use PyTorch or TensorFlow or JAX or other libraries. Except for neural networks, mostly what you're looking for will be in scikit-learn. So please attend this Thursday if you don't know how to use scikit-learn. Right, so we talked about the hierarchy of artificial intelligence, AI, and machine learning and deep learning. So I won't be talking about it again. And the reason for people using deep learning, one was the performance. We talked about how great the performance was regarding ImageNet challenge. And another strength of deep learning was less feature engineering, as it says here, less feature engineering. So we don't have to possess as much domain knowledge as before for tackling a specific problem. For example, for image classification, before deep learning, we had to be a vision expert to think about how to extract features from images. Before deep learning, but nowadays, people just dump images into CNN, or these days, not even CNN, they dump things into vision transformer, right? And for NLP, such as like translation, if you wanted to tackle English Korean translation, you had to speak both languages at the same time in order to at least give it a try. But now you just need a parallel corpus, one side English, another side Korean, and you just need to dump them into a sequence to sequence model, RNNs or transformer, and then you already have a working translation model, right? So no longer domain knowledge is needed as much as before. So could be a good thing, could be a bad thing. So we'll skip that. So in machine learning, largely there are 3 categories. So one is supervised learning, another unsupervised learning, reinforcement learning, and hopefully most of you already are familiar with the high-level concepts. So supervised learning is learning a function that maps an input x to an output y. So you have an x and y, and you just want to learn a function that can convert one to the other, So image classification, for example, is given an image, which is an x. So x is an image in image classification. X is an image. And y is, for example, if we're classifying an image into dog or no dog, a binary classification, then the space of y, output space y, is just it just consists of 2 elements, dog or no dog. And the space of images is basically infinite. If you think about 256 by 256, for example, image, then you have a 256 by 256 by 3, which is RGB, then your space is basically what? It's 2 to the 64 times 3. What is that? So yeah, anyway, 64K times 3 dimensional space. So you're dealing with a 64,000 times 3 dimensional space. And so each element so each pixel is going to be independent dimension. For example, like all the pixels in your image, it can have different intensities of pixels, usually between 0 and 255, right? So your space is very, very large, and within like this entire space of 64,000 by 3, you have a lot of images, and some images are real, like some images are cat, dog, people, airplane, bus. Some images are unreal, like total white image, total black image, or total gray image, just some, Gaussian blur, or some like some noise, right? So anything can go into this space, but only a very small subset of this space, very subset of this space will be real images. And what you want to do is you want to learn a function that maps mostly that maps one real image to either dog or no dog, right? So you need a function that does that. And same goes for any, supervised learning problem. Translation, you have X become, for example, like English to Korean translation. Then in that case, X becomes the space of English. So all English, all sentences in English. It could be a sentence, it could be a word, it could be a paragraph, it could be a book, it could be a series of books, it could be anything like it. So the space is infinite, right? So anything in this space, any element in this space, you want it to be translated to Korean. And obviously the space of Korean, this is also infinite. This is an infinite set. You need to learn a function that maps one element into another. So that would be your supervised learning for English to Korean translation. All right. So next up is oh yeah, we already have that here. Then next up is unsupervised learning. So learning usually there is no Y here in unsupervised learning. You only have an input data in that sense. So you usually what are you going to do with an input data only? You're not learning a mapping function between X and Y, right? So usually what you can do with X is just learning a distribution or some kind of manifold function of data. So examples could be clustering. So you want to find out the hidden structure of X. If your oops, not this one. If your data distribution looks like this, then you could either use 4 clusters like this, or you can have 2 clusters like this, or you can have 1 cluster like this, right? So that's up to you. But anyway, what you want to do in clustering is you want to find out any hidden structure within the data distribution. So that's one. And another is low rank matrix factorization. So it's basically you want to compress data dimensionality into smaller dimensionality. So you want to compress an image. Instead of using 256, 256.3, you want to use only 128, something like that. So we're going to learn how to do that in next week in autoencoder. Kernel density estimation is, for example, you don't have a so density, I'm hoping that everybody's already familiar with probability density function, right? PDF. So when you have a data and you don't know it's PDF, you can estimate it's PDF, right? So for example, if you have a one-dimensional data and this is your plane, then if your data like here, like a lot of them here, then some here, then again, like a lot of them here. Then your data distribution could look like something like this, and then so this could be your PDF function. This could be your probability density function. And the way you estimate it is one way to do it is using something called kernel density estimation. Right. So these are the typical things you can do with unsupervised learning. All right, cool. And then last one is reinforcement learning. So in this class, we won't be learning any reinforcement learning. There is actually another course called deep reinforcement learning. So please take that course if you're interested in reinforcement learning. So reinforcement learning is a little bit special. So typical setting is given an environment. So we have an environment, E, and a set of actions, A, learning a function that maximizes the long-term reward, R. So it's no longer like mapping X and Y or learning a distribution of X, there is no input X at all, actually. You have a setting, you have a world, E, and the things you can do in that world, A, and you want to do that thing. You want to choose a set of actions, a series of actions, or maybe just one action. Maybe it's a one-step thing, or it could be a multi-step thing. So you want to choose a series of actions so that you can win as much score or much reward as possible. So the reward could be anything. Could be an example. For example, in Go, 바둑이죠, Go. Your environment is the Go board, 바둑판이죠, Go board. And set of actions is putting your stone in any position, any allowed position in the grid, right? So that will be your set of actions, and your long-term reward is either you win or lose, right? So it's 0 or 1. 0 you lose, 1 you win. So whatever you do on that board, however you put your stone on that grid, you want to win, and that's it. So it only gives you a purpose meaning the reward, and the world and the set of actions. So there is no training data. In supervised learning, there's X and Y. So the more you have of the XY pairs, the better informed you will be, or your function will be. But in reinforcement learning, there is no training data. People can use training data to initialize the function or this function. We call it typically a policy function. You can learn from the past examples, and then start from there to learn to use better actions to surpass the previous reward. But typically, reinforcement learning doesn't require training data. Atari could be another thing. Atari it's a game, right? It's like a Space Invaders or Arkanoid. So game itself can be an environment, and set of actions is your gamepad. You can move your character left and right, and then you can shoot missiles using your A or B buttons, right? So that would be your set of actions, and the long-term reward would be your score. So every time you destroy an enemy ship in the Space Invaders, your score increases, right? So you want to survive as long as possible while maximizing the score. So that would be your setup. Self-driving car, again, the environment is the world itself. After all, Tesla or any like self-driving cars, they operate in the real world. So that would be your E. And the set of actions is whether you step on the gas or brake, your transmission, and I guess and also your wheel, your driving wheel. So whether you turn left or turn right, and there are a lot of other things like the lane changing signals as well, and sometimes you have to have a wiper operating during the rain. So there are a lot of things you can do, and that makes it all the more complex. And the long-term reward is what? It's getting from one place to another. So starting from point A to point B, and while not causing any accident, not hitting people, not going off road, or turning off engines somehow. None of that. You want to go from A to B without any accident. So that would be the long-term reward. Right. So that's it. And so questions. So in reinforcement learning, so this is the setup. Can you think of any other examples of reinforcement learning that doesn't work in this specific manner? No. The setup that I just said is that we require environment, a set of actions, and a long-term reward. But there are other ways to do reinforcement learning, and very famous one actually at that. Can you think of an example? Right, GPT. Absolutely. So Subin, nice one. RLHF, yes. So GPT is a little bit weird. GPT is actually, there is no environment in GPT. It all operates on only training examples, which is weird, right? Search engine, I'm not sure. I don't know. I'm not really sure what you mean by search engine. Search engines typically operate on ranking algorithm, right? Hyperparameter tuning, actually hyperparameter tuning works exactly in this setting. I mean, typical hyperparameter tuning. I'm saying typical like Bayesian optimizations or that kind of stuff. They usually the environment is the machine learning model, and the set of actions is choosing the values for hyperparameters, and the reward is your loss function. So you can try a bunch of different hyperparameter combinations and look for the right combination to minimize the loss, or which is actually maximizing the long-term reward. I think the user's click is a reward. You can set it like that, I guess. That would be another thing. So that would be like additional thing, but you can't build search engine only based on users clicks. Searching the fast algorithm. Yeah, well, actually, yeah, we won't go into all the details. But anyway, so as I was saying, GPT, as you are already familiar with, RLHF it works in a different manner. So it only works on training examples. So training examples meaning GPT generates a bunch of stuff, and then there are people who actually annotate the score, give them the scores, like grading them. Like this is a good response, this is a bad response, this is like neutral response. So there are people who hired by OpenAI to grade them one by one, so that becomes a sample or training sample, and then we train GPT to maximize that grade somehow. So the spirit or the algorithm itself is reinforcement learning. It's just that it doesn't require an environment. So, which would be in theory, actually being able to run around in an environment using your set of actions is like typical reinforcement learning, or maybe like ideal reinforcement learning, because you can do whatever you want in that space. You can try different stuff and then get a reward immediately. But in GPT style, the training data is fixed, so you cannot explore meaning running around in the environment. You cannot explore as much as you want to. You only have like fixed number of training samples. Like I think in GPT, ChatGPT, I think it was like 30,000 to 50,000 examples, which seems like enough if you look at ChatGPT. It works pretty well. For GPT-4, I'm not sure how many training samples there were. All right, moving on. Chat history as an environment in ChatGPT. Chat history. Actually, environment for GPT is the chat system itself. It can interact with people on real time. Yeah. I mean, you talk to ChatGPT, and then ChatGPT talks to you, and then a thread of chat is created. So that is actually environment itself. And then sometimes you can, if you want, you can click the thumbs up and thumbs down, right? But just because you click thumbs up, it doesn't get automatically work as a training signal to ChatGPT. It doesn't work in real time. Maybe OpenAI will collect your feedback and then use it or not. It's up to them, and it works in the same manner as the situation where I described, where OpenAI hire a bunch of people and then creating a training example. So basically, you're giving them a training examples by clicking thumbs up or thumbs down, but it's not traditional reinforcement learning like this. All right, moving on. So yeah, lines are a little bit blurry between generative models and self-supervised learning. So for example, in generative model, you typically maximize the reconstruction loss. So your X and Y are the same thing. You put in an image, and then you want to somehow reconstruct that image using a generative function such as VAE, right? So in that case, you don't need a separate label. You don't need like another Y prepared by like annotators. You just need an image itself. But still, you are still learning a mapping function between input image and the reconstructed image. So it seems like it could go both ways. Self-supervised learning as well. Like in BERT, well, we haven't learned BERT yet, but like BERT, you typically remove some portion of the words in your sentence, and then you try to reconstruct them using transformers. So again, you don't need a separate y, but still you are trying to reconstruct the sentence itself. So the sentence becomes x and y at the same time. Right? Yeah, all practice in this course are either supervised or unsupervised, as I said, so we won't be doing any reinforcement learning. And in all cases, regardless of whether it's supervised, unsupervised, or reinforcement learning, you're training your model or function. I just said a lot of times in function, like mapping function between x and y, or estimating function for x, or some function that maximizes your long-term reward. You're learning some function, and we call that we use like model or function interchangeably. So, and you need full x actually without this. We don't. Not for this one. Not for this one. For SL and UL, you need to learn from data. As I said, in reinforcement learning, typically in traditional reinforcement learning, you don't require training data. You only need an environment and set of actions and some kind of reward. So in supervised learning or unsupervised learning, you need data. So that is why it's called statistical machine learning. You're learning from data, and the way that you train your model is based on statistical theories. Question from An Young-jin: how is semi-supervised learning different from supervised? Actually, it's somewhere in both. So it's not so different. It's just a combination of two. So you have very small amount of label data, meaning that you'll have very small amount of x and y pairs, and you have bunch of x's without any y's. So, and you want to make best use out of all those small x y pairs, and some also leverage the unlabeled x's. So that's semi-supervised learning setting. I heard the term probabilistic machine learning. What is the difference between statistical? Not really sure. Statistical machine learning is basically modern machine learning. As I said, you're training your function, you're training your model using statistical methods. So usually maximum likelihood, or there are other ways to do it also. There's like true Bayesian optimization, or maximum a posteriori optimization as well. But usually in deep learning, we usually turn to maximum likelihood. Probabilistic machine learning, I'm not really sure. Maybe you're trying to learn a function that gives you a probability. Anyway, as I said, you want to train your model or function. It's the same thing. So train function, and your function is, if you think about it like a function, any function, your quadratic function, for example, you have ax squared plus bx plus c is your y. If you recall what you learned in middle school and high school, then you have x, which is your variable, y is your output, and these a, b, c's are your coefficients, right? 한국말로는 개수라고 그러죠, 개수. So those become your a, b, c. Your coefficients become this. So your theta. So x is your variable, and theta is, for example, in quadratic function, becomes our thetas are the a and b and c. So you want to learn them. You want to train them. So the values of a, b, c determine the shape of your function, right? If you think about a being 1 and b being 0 and c being 0, then that becomes your this. So this is where a equals 1, b equals 0, and c equals 0, right? But it could be anywhere. It could be like this. It could be this, they're anywhere, but depending on the values of ABC, right? So the values of ABC, or the values of coefficient, determines the shape of your function or the behavior of your function. So, and you don't want any ABC, right? You want to have a specific values for ABC, and those values and that value and the specific value, or the specific you need to have a goal, basically. So objective, and we call it objective function. So out of all the values of combinations of ABC, out of all the infinite possibilities of ABC, like this, like this, like this, you want to have one function that meets your objective, that satisfies your goal, right? So what would that goal be? It could be in dog classification, back to the binary classification example. The objective is correctly classifying dog or no dog. So that would be your objective. Given any image, if it's a dog, you want to classify it as a dog. If it's not a dog, you want to classify it as a no dog, right? So that would be your objective, your objective function. So out of all the ABCs, so I forgot to mention that typically your range, the range for your parameters is negative infinity to positive infinity, right? A could be anywhere in this range. So A is any real variable, right? So, and out of, or and that also goes for B and C as well. So there are infinite possibilities of your in choosing your coefficients, and you want the ones that correctly classify dog or no dog. So this is just plain words, right? But we need to mathematically formulate it. So we typically use something called loss. So loss is the opposite of succeeding your task. So loss is, for example, here I've written it as a loss as like a function name. Loss y comma y prime, and y is your true class. So in this case, y is dog, and y prime is your output from the output of the output from your function. So as I said, the behavior of the function is determined by your coefficient. So if you change your coefficient, if you change your ABCs, then the output will also change. So you want a specific set of ABC that also gives you dog when this is dog, and when the y is no dog, then you want a specific ABC that generates or that produces y prime as no dog, right? So that's what you want. So you want to minimize your loss. So if your y and y prime differ, then that's a loss, right? If your prediction y prime is different from your true y, then it's a loss for your function. And so that is why. And if they're the same, if the true class and your predicted class are the same, then there is no loss. The loss is zero. So you want to minimize zero loss, right? You want to minimize your loss, because the larger the loss, that means the more different your true class and your predicted class are. Right. So in binary classification, the loss that we typically use, so loss is an abstract term. It could be anything, right? It could be cross entropy, it could be it could be mean squared error, it could be mean absolute error. There are a lot of different loss functions. But in this case, in binary classification, we typically use cross entropy. Okay. So we'll talk about the meaning of this formulation in next week when we talk about logistic regression and MLP and all that. So basically, you have y and y prime. There are two classes. So when y is 1, when y is dog 1, then this term survives. When y is 0, when it's a no dog, then this term survives. And that's how it works. Right. So as I said, yeah, hopefully we're all on the same page where as regarding the big picture. Big picture is you want to train your function, and your function, the behavior of your function is determined by coefficient. And out of all the coefficients, you want to specify a function. You want to like converge on a function, or you want to specify a value of coefficients that meets your criteria, meaning that satisfy your goal, which in this case it was this goal, this loss function. So that is where the optimization comes in. So you want to by changing your theta, by changing your A and B and C, you want to minimize this function. So this is y prime, right? So you want to minimize this function. So that is why it's called the optimization process. So optimization meaning you have a function and you want to either maximize it or you want to minimize it, right? So if you have well, actually, yeah, we'll get to the example later. So this is optimization. Optimization meaning you have a function and you want to, by changing its parameter, by changing its coefficient, you want to maximize its value or you want to minimize its value. In this case, we want to minimize the loss function. So this is where optimization theory comes in. And if you are from ISYE, 산업공학과죠. If you're from 산업공학과, then you must be very familiar with the optimization theory and all that. Right, so there are, as I said, there are other loss functions. We only talked about cross entropy, but there are other loss functions for different tasks. For regression tasks, you can use either mean squared error or mean absolute error. And if you're using translation, then you are using the input sequence and the output sequence can vary all the time. There is no fixed size, right? So theoretically, your function needs to deal with like varying length of input and output sequences. So, but typically we use like sum of negative log likelihood. And in GAN, like for example, in GAN there are other optimization. GAN uses other objective functions. So there are a lot of different objective functions. So how to optimize your model? So find x that minimizes this function. As I said, we were talking about a quadratic function. So find, actually, this is a little bit different because so far what we talked about is changing your values of A and B and C, right? So in that case, the A and B and C were not determined, were undetermined, and we wanted to, change the values of A and B and C to change the shape or the behavior of your function. But in this case, how to optimize your function, this is just a very simple background explanation of how you would like change the value of your output function, so of your function. So bear with me. So already here A and B and C are fixed. A is 1, B is -2, and C is 1. So sorry for the confusion, but here the things that we're changing is x. So if we have such a function like this, then you know that x equals 1 is the one that minimizes the output of this function f, right? When x is 1, then the output, which is fx or y, is at the minimum. And we know that. So we know that this is the global minimum. Out of all the places, out of all the values of this function it can have, there's only one place that gives you the minimum. So it's a global minimum. It's a minimum everywhere, right? So the question is, why one global minimum? How do we know that there is only one global minimum in this function? Right, it's a convex function. So 응유엔, so very good. It's a convex function. Gradient is 0 is not actually the right answer. So it is a convex function. The function looks like this, right? So actually I need to, function looks like this. Actually, sorry, I should draw it a little bit better. So there's one here, and this is 1, so this is not perfectly symmetrical. Anyway, it's something like that. So function is convex, so any local minimum is also global minimum. That's also a right answer. All right, so when x equals 1 is right here. This is where x is 1. So this is the lowest point in all the places, all the places in your function. This is the lowest point, and nowhere else is lower than this point. And we know that there is only one because it's a convex function. It's a quadratic function, right? So if the function was concave function, then we know that there is only one maximum point. So a follow-up question: how do we know that some function is convex or not? First diff is 0. Not really. Second diff is 0. Not really. Yeah, the second gradient is larger than 0. So that's the correct answer. Second gradient, the second order gradient or the second order derivative should be larger than 0. That is how we know it's convex function. So for example, here, if we have double gradient, then it becomes what? It becomes 2. So it means that it is always increasing, So that means it's convex. So in a multidimensional function, we would have to get a Hessian. So that becomes very more, all the more complicated. But that's one way to usually define that whether your to determine whether your function is convex or concave for that matter. So moving on. So that was very easy for this guy, because this is a very simple function. We already know its form, right? But in this loss function, for example, if you think about the image classification, dog or no dog, then the loss was cross entropy, and your function could be anything. It could be CNN, it could be transformer, it could be whatever you want. It could be any function. So the mathematical form would be way more complex than this guy. So the loss is complex, not meaning imaginary. It's just complicated. The mathematical form of your loss function will be very, very complicated. And typically it's non-convex function. So we don't know that there is only one global minimum or not. There could be many, many local minima. Local minima meaning like if your function looks like this, then there's local minima here, 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 right? So yeah, I guess I don't need 3 races. So there are many local minima, and there's no analytical solution. For this guy, we have an analytical solution. We just need to set this to gradient 0. Then you get the minimum point, right? But in this guy, typically, which again, as I said, your function could be anything. For example, if you have GPT, like 96 layers of transformer, and you're doing some kind of, I don't know, like next word prediction, then no way you can analytically solve it. You have to numerically solve it. So the way that you do it is, as I said, numerically, you want to employ a numerical method. So numerical method, typically strategy is to iteratively find a better theta until you're satisfied. So you start with some theta, you start with some random theta, and then you evaluate your loss function, whether your loss function is low enough, and if it's not low enough, then you estimate another theta, and then you evaluate your loss function. If it's lower, the better. So this is typically so typically we call that numerical method a gradient descent. So you're updating your theta, your ABCs for that, for example, you're updating your parameters theta based on your training data X and Y. So this is all based on, so you have a training data, you have like a bunch of images, and you have dog and no dog labels for each image, and you have a loss function, which is loss function meaning cross entropy. So you have all the things you need, you have all the material you need to optimize your parameters, your coefficients. You have the data, you have the objective function, and then you have the function to optimize, then you have everything to go. So if your loss landscape looks like this, so this is we're assuming that this is a 2-dimensional function, or sorry, 2-dimensional. Yeah, we can call this a two-dimensional function. So there's, let me draw it a little bit better. Like this, and you have your theta 1 and you have theta 2. So this is your coefficient, theta 1 and theta 2. So your function is, for example, like could be a linear function. Your function is theta 1. Oops, I accidentally. Theta 1 x plus theta 2 is your y. Is your y. You can think of this function as like 2-dimensional function. So there's one axis for theta 1 and another axis for theta 2. So by changing the values of your theta or coefficients, your function changes, right? The behavior of your function changes. And what we're doing here is, so what is this concentric circles? What is this? This is the loss function. So you have a loss function. You have your y, the true label, and you have your predicted label. So this is actually your y prime. And your loss function is also a 2-dimensional function because it's based on your thetas, right? So, and at some point, somewhere in this 2-dimensional, in this 2-dimensional space, this is actually the lowest point. in loss function. So actually, you can think of having a three-dimensional space like this. Three-dimensional space. This is theta 1. This is theta 2. This is your loss value. And as you move around, in this plane, well, I'm not a very good drawer, but as you move around in this two-dimensional plane, this theta 1, theta 2 plane, your loss changes. Your loss, in this case, I guess this is a convex. Your loss is like this, right? So as you move around here, you know, like, and you can move around anywhere in this theta 1, theta 2, and you want to be at this place where theta 1 and theta 2 are like this, right? Because this is the lowest point. This is that lowest point. So by moving around your theta 1, theta 2, hopefully you will get here, which is where the loss function is at the minimum, right? So, and you want to do it, you can't solve it analytically, so you have to take it, you have to take an iterative step. So that is where these arrows are depicting. So you start from x0, so this is your first set of values. So this is your theta 1, theta 2 values at step 0, right? And then you evaluate your loss function here. It's pretty high, right? It could be like here, and then hopefully you will get to a better direction here next time you go here, and then you went from here to here, so your loss is smaller, and then you go to here, inner to, you know, like lower every time. So at x4 you are nearly at the minimum, right? So that is, so you start from here, which you have a specific values for theta 1 and theta 2, and then you're here at another specific value for theta 1, theta 2, here, then here, and then lastly you're here and here, right? And hopefully at some point you will get to here and here, where theta 1 is like this value and theta 2 is this value. Then you're at the minimum. So that is what gradient descent is. And so you're updating your parameters based on your training data xy. So you can see that, let me erase. There's theta k and theta k plus 1. So theta k plus 1 is, for example, x4 is like theta k plus 1. X3 is your theta k, right? So this is your current set of coefficients. This is your next set of coefficients. And the way you update your parameter is based on the gradient of your loss function, gradient. So gradient meaning that if you're here, then your gradient is going downwards, right? Your gradient is negative. So you take that, you go to that direction here. So that direction meaning you want to go to the gradient, you want to minimize your loss function, right? So you take the negative some step. So this eta is some step. It could be 0.1, 0.01, 0.001. It's up to you which value you use for eta. If you use a large eta, then you'll take the gradient step like this, you know, like large steps like this. If you have a very, very, very small eta, then your gradient steps will look like this. So the smaller the gradient, probably the safer, because if you use the smaller the eta, then probably the safer, because if you use like a very large eta, then suppose that you were here and your gradient direction was here, then if you use a very large eta, you will go here, bypassing your low point, right? So you'll go here, you'll go here, you'll go here, you'll go here, like you'll just oscillate, never reaching the minimum point. So you want to use a sufficiently small eta. But if you use too small eta, then you'll never get anywhere, because you'll go here, here, like this. It'll take forever to get to the bottom. So you want to use like the appropriate value for eta. So that's the whole point about this equation. Your next set of parameter, your next coefficient, is determined by your current coefficient minus the eta, the step size, times the gradient of your loss function. Hopefully this is very, very clear. Right, so that was it. And typically we use something called stochastic gradient. So this is gradient descent. This is stochastic gradient descent. So stochastic gradient descent. So this is SGD is what modern deep learning is founded upon. And we call that stochastic gradient descent because we don't use the entire y and x here. Here, we were assuming that all y and x were used to draw this loss function, draw this loss landscape. But typically in deep learning, because your training data is too big, it doesn't fit on your memory. If you're dealing with like trillions of samples, then you can't fit them all in your computer memory or video card, like GPU memory. So it'll blow up your RAM. So you only have to, you have to sample very small amount of training data, like maybe 64 samples at a time or 128 samples at a time. So there's sampling involved. That is why it's stochastic, because you randomly sample from your entire data, like very small portion, like, well, as I said, 64, 32, or even 8 samples at a time. You sample them. So that is where stochasticity comes in. So it doesn't fit on your memory. It takes too long to calculate the gradient. So you take a very small amount. So every single time you sample a new mini batch being 32 samples a time or 64 samples a time, every single time you sample a new mini batch, your loss landscape changes a little. Sometimes it looks like this. 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 Like your loss function changes because your x and y changes every single time. So that is why it's stochastic. It randomly changes. It is perturbed very like I don't know how much. We don't really know, but depending on how you sample your data, your loss landscape will change. And so if you can imagine, if you sample too small amount of data, if your mini batch is too small, for example, extremely like 1, if you sample 1 sample at a time, then your loss will change drastically by each sample. But if you choose like enough, like if you sample 100 samples at a time, then your loss function will change less, like this. It'll be a little bit more stable. Right. And yeah, sometimes smaller batch size helps you avoid optimal minimum, because as I said, your loss landscape changes by your mini batch. Sometimes it is helpful because sometimes your training process will get stuck in some local minima, and if you shake that landscape a little, then you can get out of that local minima. And there is a premise: your mini batches have to be sampled IID, independently identically distributed. So you have to randomly sample from your entire data each mini batch. Otherwise, if there's like some kind of dependency between mini batches, then your SGD will not be the same as GD. So stochastic gradient descent will only give you the same solution meaning the values for coefficient. So SGD solution and GD solution being the same, that is all conditioned on when you sample your mini batches IID. If you do not randomly sample, then your SGD solution will not be the same as GD solution. As I said, modern deep learning found in SGD. So the question is there any criteria to say that the loss value is minimum enough to stop iterating? Good point. We're getting there. How do you know when to stop SGD? Because you can't optimize forever. You can run your SGD forever, and it'll keep updating your coefficients very small amount, but we don't have like forever. We have to finish our training in a moderate amount of time, right? So using the value of your loss function, for example, should we look at the loss value and see, okay, so this loss value is enough, so I should stop my SGD? That is, you can try to do it. You can do it theoretically, but it's not very intuitive because your loss value is like typically like very small amount, and you don't know if 10 to the -3 or 10 to the -4 or 10 to the -5 is like sufficient or not, because the loss function is not very intuitive. So it's really hard to choose when to stop your training by looking at the loss value. So we have other ways to evaluate the performance of your model, performance of your function. So typically in classification, we use something called accuracy. If we're going with binary classification, then we can use something called AURC or precision or precision recall. So these are other ways to evaluate how well your function is performed. So accuracy meaning like if you correctly classify the sample to dog or no dog. So if your accuracy is like 99%, then you should be pretty satisfied. So if your model performance is like above 95, then you can stop training your model, something like that. Like you set your own criteria. You decide when to stop, but instead of using loss function, loss value, you use these popular metrics to decide when to stop. So precision recall, blue score, perplexity, FID score, like these are all very popular metrics, and we'll take a look at them. We'll take a look at a couple of them next time. Right. And before we get into another thing, we should talk about splitting your data set into 3 parts: training and validation and test. So splitting the entire data set into 3 sets. So training set is the one that you use to train your model. And validation set, sometimes it's called development set, dev set. Use this to use this dev set or validation set to evaluate your models. Evaluating meaning this evaluation, when to stop your SGD. So using your training data to evaluate your function to know when to stop is a bad idea. You should use another set of data, which is the validation set or development set. I'm going to call them validation set from now, which is your validation set. You use this validation set to decide when to stop. So you use this validation set to evaluate either accuracy or blue score or whatever, to evaluate your model and decide when to stop training. And the test set is the unseen set. So this is unseen during training. This is used for training. This is used for evaluating during training. So these two are seen during training. And test set is the one that is never seen during training. It is used at the one final step when you've decided when to stop your SGD. When you've finished your training for good, then that's when you use test set to evaluate how well your model is doing, how well your model is generalizing to an unseen set. So that's the one last. So the important thing is don't ever use this set. Don't use this set during training because that would be cheating. The test set is the one that you use for the one final time. Question from Daniel. What does the parameter update look like in the unsupervised training? Well, actually, that's a good point. Also, there are appropriate loss functions for learning your unsupervised training your function in an unsupervised manner. For example, if you're going for clustering, then well, actually, we're going to talk about clustering, so we can get to that later. But anyway, there is a corresponding loss function. It's not really a loss function, but it's some objective that you want to satisfy while doing unsupervised learning. For example, in clustering, you want the clusters to look inside the cluster, the intra-cluster samples to look homogeneous, and interclusters to look heterogeneous. That's the point of the clustering, right? So you can formulate them in a mathematical manner, and then you can calculate the scores for that. So while you're updating your cluster parameters, you can look at the scores and then see when you're satisfied. Right. Question from 연재 Kim. 트레이닝에 사용하지 않은 밸리데이션 세트 언신해 볼 수 있지 않을까요? 아니죠. 트레이닝에 사용하고 있죠. 왜냐하면 학습하는 동안에 계속 중간중간에 밸리데이션 셋으로 내 애큐러시가 얼마인지 체크할 거거든요. 그러니까 뭐 100번에 뭐 100 이터레이션에 한 번, 뭐 10 이터레이션에 한 번, 1000 이터레이션에 한 번, 이런 식으로 중간중간에 한 번씩 이벨 셋을 이용해서, 아니 그 밸리데이션 셋을 이용해서 내 애큐러시가 몇인지를 보고 그 다음에 이제 대충 이쯤이면 됐다. 그러면 이제 학습을 끝내는 겁니다. Right, so and now we come to something called n-fold cross-validation. So testing your model's performance in diverse training. So the whole purpose of n-fold cross-validation is testing your model's performance in diverse train-valid test splits. So for example, you have entire data, you have like this amount of data, and you use this for training, and this for validation, and this for testing. But this is just one split. You can also split this same data like this. Like this could be your training, this could be your testing, this could be your validation, right? It could be anything. It could be any split. So if you have a fixed amount of data, which is this box here, then probably a good idea to split it multiple different times to see how well your model is trained, right? Because there are different combinations for train, validation, test sets within given the same data set. Right. So in this case, we're looking at n equals 8, 8-fold cross-validation. So that means that you split your data, your entire data into 8 parts. 8 parts. And one part becomes your test set. This is the unseen test set. And then the remainder 7 segments become your training set. And probably you want to use some of these, like subset of this 7 segments to be the validation set. For example, you can set this amount to be validation, and this could be your training. So that is when your first segment becomes your test set. But this in the same manner, this could be your test set, and this can be your training set. So each segment can be your test set. So that is why we call it 8-fold cross-validation. We have 8 times, we split this 8 different times to train your model and then test your model. So you train your model on this and then test on this. Next time you train your model on this. Oops, this is weird. Okay. You train your model on this and then test on this. So that would be fold 2. Fold 3 is you train your model on this and then test on this, and then repeat and repeat, rinse and repeat. So you do it 8 times. So that gives you a better statistical stability to evaluate your model. So because, for example, if you use only 1-fold cross-validation, if you only use this for testing your model, maybe this test set was so easy. You got lucky, and then all the samples within this test set were so lucky that so your model got a really good test score, like 99% accuracy, which is just lucky. It's just purely, it's not really that the model is generalizing well to unseen test set. It was just pure luck. So that is why you do it 8 times. You test on here, you test on here, you test on here, here, and you won't get lucky all the time. So you average them out, and then you will get a more statistically reliable model performance estimation. So that is where n-fold cross-validation comes in. So there was question, 박재현, validation set도 미니 배치에 포함되어도 되나요? 안 되죠. 네, 미니 배치 포함되면 안 됩니다. 미니 배치는 트레이닝 셋만 하는 거죠. 밸리데이션은 트레이닝 셋 업데이트, 그레이디언트 업데이트가 끝나고 하는 거예요. 그레이디언트 업데이트가. Is there ideal ratio or commonly used ratio to split data for? No, not really. There is no. Usually we use something called 8 to 1 to 1, 8, 1, 1. If your data is like 10, if your data is 10, then we split it to 8, 1, 1. So this is your train, this is your validation, this is your test set. But there's no like fixed rule. Question from Kwakjo: when you are training each fold, do they get to initialize? I'm not really sure what you mean. Yeah. Is there any typical value for n in n-fold cross-validation? Usually we use 5 cross-validation. So 5 is usually enough. When you're training each fold, I guess when you're training each fold, you initialize your function. So this is starting from scratch every single time. So you start from scratch from using you train a whole new function based on this training set, and the next time you train a whole new function based on this training set. Then the next time you train a whole new function using this set, rinse and repeat. So yeah, and this n-fold cross-validation is not often used in modern deep learning. So like people still, I mean, it's a very good practice to use n-fold cross-validation because it gives you a much better estimation of how well your model is doing, because you're not testing it only one time. You're testing it n number of times with different combination of train, validation, and test set. But modern deep learning, the data set is too large. So if you have like trillions of samples, then if you want to run like 10-fold or 5-fold cross-validation, you need to train your model 5 times. Basically, when you do n-fold cross-validation, you need to train your model n times. So when it takes for you to train one model a month, then when you are doing like even 5 cross-validation, you need to run it for 5 months. So it's not really realistic, right? Like, for example, you cannot imagine doing n-fold cross-validation using GPT, right? GPT takes like months to train, and you can't do n-fold cross-validation for it. Question, so if we use n-fold cross-validation, the training time is n times more than, yes, that is true. From Cedric, I think cross-validation is mainly used with small data set when gathering data is complicated or expensive, like biology or medical data. True, but it is always good practice to use n-fold cross-validation, even when your data is like not so small. But if it's gigantic, then it's practically, realistically impossible. From Cecilia, after you start from scratch many times, do you just pick the best result, or do you? No, this is every single time counts, because if you're familiar with statistical theory, the larger the sample, the more reliable your estimate is. 그러니까 뭐냐? 통계 추정을 할 때는 샘플에 she's Cecilia. I'm sorry. Yeah, it's probably I better explain this in English. So when you want to estimate something in statistics, the larger the sample size, the more reliable your estimate is. Reliable meaning your variance of your estimate becomes smaller, right? If you're estimating, for example, like the average height of Korean male, then if you only look at 5 males and then, okay, they're like 170 centimeters, that is very, very unreliable estimate. You need to look at the larger the sample size, the more reliable, the lower the variance of your estimate is. Same thing here. If the more you split your n-fold, if you go from 5-fold to 10-fold, then you have more sample size. Your sample size has increased double. Then it means that your variance is way smaller. The variance of your estimate is smaller. The estimate meaning your test performance of your model. All really matters is how well your model performs in test time. So that is a test performance, like test accuracy, test perplexity, test FID, test blue score, whatever, your test performance. So you want to get an accurate, reliable estimate of your test performance, and the larger the sample size, the better. Hopefully that makes sense. From question from 김정희, n-fold cross-validation 경우는 파라미터 자체를 평균된 방식. 아니, 제가 지금 얘기한 거 들으셨죠? 그거 아닙니다. Right. So question, data. So as I said, modern deep learning typically don't use n-fold cross-validation because data set too large and time consuming. And I put it here, statistically unnecessary. So what does it mean, statistically unnecessary? Why in modern deep learning, where data is so large, why is it statistically unnecessary to do n-fold cross-validation? Any takers? Love large number? Not really. That's not. 우정. If data is large enough, it meets IID. Okay, I'll get that. I'll give that a point. Because the variance is low enough. That's also a good answer. Yeah. So if the data is large enough, it's almost IID, or the variance is low enough, meaning that if you're training, for example, if you take the entire, for example, the ChatGPT is trained on the entire internet, meaning that it's trained on population itself. It's not trained on a sample of population. It's trained on all possible data out there. Like the entire distribution of human language is basically on the internet, right? So when you have that, then when this is your entire internet, this is the internet. This is the internet. And then ChatGPT is trained on like this. Let's assume that this much. I mean, ChatGPT didn't have test set, but still, let's assume that it had test set. So like 90% of the internet and 10% of the internet. So 90% was used for training and 10% was used for tests. 10% of the entire internet is already large enough to represent the entire distribution of the data. 10% of the internet is, again, so large it can work as a representative set for human language. So that is why we don't need that. We use n-fold cross-validation because we are not sure, as I said, if this test set was lucky that all the easy samples were here, or maybe unlucky, all the hard samples were in this test set, so that your test performance estimate was not reliable. But if your test set is so large, like the 10% of the internet, then it already gives you a reliable estimate of your test performance. So that is why you probably don't need it. So if you have a lot of data, if you have like basically basically all data, then you probably don't need n-fold cross-validation. Right, moving on then. So a bit more to the technical side. Overfitting, underfitting. So hopefully already a lot of people are already familiar with overfitting, what overfitting, underfitting is. But this is a very good illustrated example of overfitting, underfitting. So assume that your true data, so your true function is this guy, and you have samples from them. You have samples with some noise. So there is like very small amount of noise, like here. This is a noise, and this is also noise. When you observe from the true data distribution, true function, it usually comes with a noise. For example, if you're using a sensor to measure the temperature or whatever, like wind power or like wind velocity or something like that, then usually sensors have observation errors, right? So this is that noise, the observation errors. Right. So this is your true data. I'm sorry, this is your true function, and you have observation. So this becomes your training samples, and you want to estimate this. You want to learn a function that estimates this true function. And for example, let's say that you use linear function. This is not a good idea because you have, well, I mean, in this case, we already know the ground truth function is at least cubic, I guess, like third order, at least third order. So we already know that since the ground truth is third order function, linear function is not good enough because it already gives you like large errors. Like in this region, there's a lot of error in this region. So too much error or too high loss, because we use loss function. So the loss is too high. So your MSE, your mean squared error loss, is like 0.4 in this case. If you use higher capacity function, instead of using linear function, you use a degree 4 polynomial function. So ax4 plus bx to the 3, cx to the 2, dx to the 1 plus e is your function. Then this is your degree 4 function, right? So you have a, b, c, d, e to estimate. So you have 5 coefficients to estimate. So if you do a good job of doing that, then your function, your degree 4 function, will be very, very close to your true function. So your blue line. Oops. Oh man. Okay, sorry about that. We were here. So your blue line is almost the same as your orange line. So your fourth order polynomial function is as good as the true function. So that's like the perfect fit. But if you go overboard, if you this is an overkill. If you like you can think of like you can imagine, okay, the powerful the function, the better. The higher order, the better, because that means you have more coefficients. It means you have more degree of freedom. It means that you can be more flexible. You can learn anything you want. So this is the result of your function learning anything you want, because it has so high degree of freedom. It can hit all these samples very, very accurately. Like it is just piercing through all those nitty-bitty details, which is unnecessary because, as I said, all training samples come with a certain level of observation noise. There's observation error, and this function is too powerful, so it is learning all those specific noises, and now it's just doing a bad job all over again. So this is the underfitting. When your function, your model is too low power, then it's underfitting. This is overfitting. You are using too powerful a function. So you should use right amount of power, which is degree 4. But this is easier said than done. Because you don't know the ground truth function, actually. Question from 박명. overfitting 혹은 underfitting 발생하지 않는 모델의 파라미터 크기 데이터셋 할 수 있나요? 할 수 없습니다. 왜냐하면 데이터셋의 크기랑 관련 있는 게 아니라 데이터셋의 컴플렉시티랑 관련 있는 거예요. 이게 지금 그 3차 함수라고 보면은 여기에 3차 함수에 점이 몇 개가 있는지가 중요한 게 아니죠. 점이 하나만 뭐 이렇게 점 한 4개만 있어도 뭐 대충 3차 함수라는 걸 알 수 있잖아요. 그러니까 이제 그 점의 개수가 중요한 게 아니라 점들이 나타내는 분포의 그 스트럭처가 중요한 겁니다. How can you choose the right degree of model? Exactly, as I said, it's not really easy. You usually it's dark magic. You learn from experience. But in modern deep learning, we don't care about that. Interestingly. Overfitting to training data. So this is another important concept. As I said, what we are after is the test performance, not the training performance, because as you train your model, when you use a sufficiently powerful model, powerful model meaning like degree 15, if you only look for training performance, then you can easily get zero error, meaning like zero loss. You can get perfect fit if you use powerful in a function, like perfect fit meaning like this is perfect fit. Like loss here would be very, very minimal. Like training loss, I'm saying. Training loss, when you use degree 15, training loss would be smaller than when you use degree 4, because degree 4 is not hitting all the nitty-bitty details, right? But here it's hitting all the nitty-bitty details. So training loss for degree 15 would be smaller than training loss for degree 4. But that is not a good idea, because as you increase your model complexity, meaning that the polynomial function, the higher order polynomial function, your training error will keep decreasing. Like from here to here to here, your training loss decreases, but your test error or test loss or test performance, let's say test performance, your test performance will decrease at some point, meaning your test error or test loss will start increasing at some point. So if you increase from 1 to 2 to 3 to 4, your test error will also decrease. But if you go overboard from 5 to 6 to 7 all the way to 15, then your test error increases. So that is what is this graph is trying to tell us. There is some point where that is the optimal point, optimal model complexity point, and in this case, it was degree 4. So you don't want to go overkill. You don't want to go overboard. So if you try to increase the model complexity and try to maximize your training performance, then it'll not generalize well to unseen data, because you will start overfitting to these very small observation errors that are only in the training samples. So please keep that in mind. So overfitting, underfitting. So there are some remedies. So when your model is underfitting, meaning that no matter how longer you're trained or how much data you use, you're not just getting the right amount of performance. Like your accuracy is always like 70% or 75%. Then consider complexifying your model, meaning that you use more powerful model. Like instead of using 4-layer transformer, maybe use 8-layer transformer, or maybe use 12-layer transformer, or add more features. That's also possible. Like instead of using like you only like I don't know features, meaning like in tabular data, you can use like choose which columns you want to use, right? So you can use more features or train longer. These are all remedies. If your model is overfitting, then try to, well, here it doesn't say that downsize or downsize the complexity of your model. It doesn't say that. It says regularize your model or get more data. So the more training data you have, like for example here, the more training data. Actually, this is not a, yeah, the more training data you have, the harder for your model to overfit to your training samples. For example, here, for suppose that you only have like, suppose that you only have like one, let me use red color, like 1, 2, 3, 4, 5, 6 samples. Like if you only have 6 samples, then, well, actually, I forgot to put observation error. So 6 samples here, like here, 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 like this. This is your 1, 2, 3, 4, 5, yeah, 6 samples. Then when you use degree 15, then it'll start working like like this, right? Just like in here. But if you had way more training samples, like millions of samples, billion samples, all everywhere you have training samples, and they all have like small amount of observation error. But still, like if you have like 10,000 samples here, then it's, even if you use degree 15, it's really hard to look at like this, because there are too many samples that this degree 15 model has to satisfy, right? So you can't really set it, you can't really make a crazy function like this when your training sample is like 10,000. So it's always a good idea to have more training samples, because no matter how powerful your model is, if you have really large amount of data, then you will always usually get the true function. So that is where this get more data is. Regularized, we'll talk about it. Yeah, we'll talk about it later. There's another thing called curse of dimensionality. So when underfitting, as I said, I said add more features here, right? But adding more features blindly is not a good idea, because if you add more features, linear increase in number of features requires exponential increase in the data sense, the samples, the data size, training size. So if you go from like one dimensional feature, meaning you have you use only one feature, going to two features, then this was a line, but now you certainly have a plane, right? You have a plane, so you need to fill that plane to properly learn your function, properly train your coefficients, right? If you add one more feature, then it becomes a space. It becomes a space, right? So now you need to fill that space to properly learn the structure of your data and learn the coefficients. So as you linearly increase your feature, you need exponential increase in your data size to fill that space. So that's the curse of dimensionality. So usually not a good idea to blindly add features. But again, in modern deep learning, nobody really cares about this kind of thing, because like if we're dealing with like language, then the dimensionality is just infinite. Yeah, still plays some role in modern deep learning. We'll get to that later. I think there were some questions. From Kim Hyun-seo, is complexity related? Actually, we're almost out of time, so I guess I'm going to have to answer the question later after the class. So regularization. So as I said, one way to deal with overfitting is regularization. And what does regularization mean? So the reason that your function looks like this, like behave this crazy, is because your coefficients have a very high value. In order for your functions to look like this really wiggly, like, you know, jumping up and down, your coefficients need to have a very high value, like, or not high, but like large in magnitude. It could be like positive high or negative, like large in positive value or large in negative value. So you want your functions to look nicely, like, you know, like nicely, like this, right? So that is where regularization comes in. So you want, in addition to your loss function, meaning your MSC in this case, loss function, you have another term that where it says that you don't want your W's to have such a large magnitude. So this is where this square term is. So you want to minimize this whole function, this whole thing. Not only you want to minimize the loss, but you also want to minimize this. So, and what does this mean? What does this minimizing this mean? It means that this is your L2 norm. Actually, it's a squared norm. So this is your norm of your W's. So it means that you don't want your W's to have such a large magnitude. So you want to penalize it. So that is why you want to minimize both at the same time, so that your values don't become like this crazy values. You want your values to be like nice, like 1.5, negative 0.3, something like that. Then your function would be very, very smooth. Maybe too smooth, like this, linear. So that's where the trade-off comes in. If you set a very large lambda to penalize this magnitude too much, then your function would look like a linear function. So that's not a good idea. So again, that is where the dark magic comes in, setting the right value for your lambda. Right. Yeah, right. Also, this is L2 regularization because we're using L2 norm. You can use L1 norm, L1 regularization, and this will actually look like this. So L2 norm, L1 norm, hopefully everybody knows what that is. And depending on what kind of norm you use, L1 and L2, what kind of norm you use, your final function, your final coefficients will look different actually. So with L2, you will get like a smooth function. With L1 norm, you'll get a very, like some values will be sparse, some values will be like 0, and some values will be non-zero. So it'll be a sparse value. And yeah, the remainder of this class is some popular classifiers. So logistic regression. Logistic regression is based on probability. So you start for probability, you convert it to odds, and then you convert it to log of odds. That's where your logit comes in, and then you model your logit as a linear model. So that's where logistic regression is born. So it's trained on gradients. We'll talk about logistic regression next week, actually. So we'll skip this one. Another popular classifier, support vector machine. This is all about increasing the margin between your one class and another class. Like basically, support vector machine is a binary classifier, and you have one class on another class, and you want to increase the margin between these two classes. So, and the one function, or the set of the coefficient value that maximizes the margin between the two classes is the optimal coefficient, or meaning the optimal function, right? So that is the spirit of support vector machines. And another thing is decision tree. I guess in this course, we won't be using any support vector machine or decision trees. Actually, no, I mean, this Thursday, we'll be looking at these examples in scikit-learn, but deep learning has not so much to do with support vector machines or decision trees. Ensemble is actually, it's not just classifier, it's a training strategy. So using multiple classifiers or multiple regression models, for that matter, to improve performance. So there's there are typically two types of in Ensemble. There's bagging, and then there's boosting. So bagging is training multiple classifiers on different subset of data. So if you have a lot of data, you use this much for training one data, this much, like this much for training one model, this much for training one model, like this much for training one model, this much for training one. Like you sample like 90% or 85%, 80% of your training samples to train like a little bit weaker classifier, and then you average them out. So that's bagging. Or you can actually you can use subset of features. Like if you have like 1,000 features, you use 900 features each time to train multiple different models, and that's where random forest comes in, right? So that's bagging. Boosting is using weak learners, so like simple classifiers like single decision tree or single logistic regression or single support vector machines. Like you use multiple classifiers sequentially. So you first train you first train a decision tree, for example, and then you will inevitably have a certain amount of error, because single decision tree is not a powerful model. So you take those errors, and then you train another decision tree based on those errors only, and then that will also incur some error. So then you take those another set of error, another like secondary or second order errors, and then you take those errors and train another decision tree, and so on and so forth. So you use like k different decision trees sequentially to deal with the residuals, deal with the errors that cannot be solved by previous decision trees. So that's where boosting comes in. It's a very, very powerful concept. It's a very powerful concept. And typically when you are in a competition like hackathon, or like, you know, whatever, like some Kaggle competition, or Kaggle, like, you know, like hackathon or that kind of stuff, usually the top rankers, high rankers, usually use ensembles. So ensemble is a very, very powerful strategy. If you want to win at a competition, you must use ensemble. And yeah, we're back to clustering. So clustering is a popular example of unsupervised learning. K-means clustering is one of the most popular clustering strategy. And so K-means clustering is like it's a deterministic clustering, and then we have a mixture of Gaussian, which is probabilistic clustering. So K-means the strategy is very simple. You first have to set the number of K yourself. Like I'm going to do 10 clustering, or I'm going to do 5 clustering, I'm going to do 7 clustering. Like the value of K is up to you to decide. And so after you set the K, you have K centroids. Centroids meaning the center of your cluster. And then you randomly initialize your K centroids, and then you repeat these two processes over and over again. You update the membership of each sample to your closest centroid, and then you update the centroid based on your membership, based on your member of your current centroids, and you repeat this process again and again until there's no change in the membership. So that's what it is. And ideally, this is one centroid, this is another centroid, right? We can see that you can see these triangles. These are the two centroids. So centroids start here, and then you update the centroid, and then you recalculate the membership. Once the centroid is here, then these should be the new member, and this should go here, right? So, oh, actually, no, I guess this was here. Anyway, you see what I mean. And when you have these centroids and the membership, you can calculate how close your samples are to your centroid. So that's like intra-cluster similarity, and how far your samples are from other centroids. So that would be interclass dissimilarity, and you want to hit both at the same time. You want intra-cluster similarity to be high, intercluster similarity to be low. So that's the whole spirit of clustering. So that becomes your objective function, or evaluation metric, to be more precise. And Gaussian mixture, you use multiple k different number of Gaussian distributions, and then you try to fit them in your training samples, and then that becomes your probabilistic clustering. So your membership is no longer like this guy belongs to this guy for 100%, but here this guy belongs to like 30% to here, and like 70% to cluster 2, and like 0.1% to cluster 3, like that. Right, so that's it. So we are barely on time, and so this is the end of the class. I'll keep staying around to answer the questions. When did I start missing the questions? So I think we start from Kim Hyun-sung. Is complexity related only to the number of hyperparameters? Is complexity related only to the number of hyperparameters? Complexity. No, not really. Number of hyperparameters? I'm not really sure what you mean. It's the number of parameters usually, not the learnable parameters, not hyperparameters. It's the how many number of coefficients there are, learnable coefficient in your function is. That usually is the like a yardstick to measure, to decide how complex your function is. Fatrina? Is it possible that synthetic data alleviate overfitting problem, considering real data is scarce? Actually, that's a very good question. We'll have to talk about that. Yeah. Let me hit other questions first, because that's a complex question. Is the reason why you said modern ML doesn't care about high degree is because we just need a lot of actually modern ML, modern theory. So this overfitting, underfitting theory doesn't really work well in modern deep learning, because in modern deep learning, what you do is usually you start with a really large function, like several stacks of transform, or really large stacks of conv or whatever, and then you train it, and then you finish the training early. So you don't train for as long as you want. So you when you train for long, then there's a high probability that you overfit to your training data. But if you train for a very short amount of time, like based on your validation performance, you don't give the opportunity to the model to overfit to the training data. So usually overfitting doesn't really happen when you stop the training early. So that's usually what people do these days. And if you have a lot of data, then there's no action. So there's two cases. When you have near infinite amount of data, which is GPT's case, near infinite amount of data, training, you can't even train for too long because it will take too long, right? You just go for one epoch. You just go through the entire training data only once. You don't go it multiple times. You only go through the entire data only once, and that is already like several months. So you don't even care about overfitting, underfitting when you have infinite amount of data. As I said, when you have fixed amount of data, like small enough amount of data, when you stop the train early enough, you probably don't you probably don't give the model an opportunity to overfit to the training data. So that's usually what people, as far as I know, that's what usually people do. Question from Ho Chongwon: How do we know which norm is better? Actually, there is no better norm. There's only a preference. Like if you want to have a sparse coefficient, you should use L1 norm. If you want to use a smooth coefficient, then you use L2 norm. And there are other norms. There's like hybrid of L2 and L1. There's like elastic net, and there are a lot of different ways to regularize. But these days, modern deep learning, they don't really care about regularization. Question from Hwang Younghae. How combine multiple classifiers to one classifier after bagging? Oh, how do we combine multiple classifiers after bagging? You usually use voting strategy. Like if you have 10 classifiers, for example, and you have a binary classification, then each classifier will give a score between 0 and 1, right? Some classifier will give 0.1, some classifier will give you 0.2. You add all those up and then divide by 10, which is averaging, and that's it. That's the voting. So or averaging, actually, that's averaging. So you usually typically use averaging strategy. And the last question, how could you explain how about the bonus points for? Oh, actually, yeah, that is true. I didn't mention that. Required amount of points. Okay, how to check my bonus? I'm sorry if you already. Yeah, okay. So actually, so I forgot to mention that each time you answer the bonus question, all the questions that I asked today will be bonus questions, by the way. But I'm only giving the first answers, or actually first answers with different answers. I'm going to give them the bonus points. Each bonus point will be 0.1. So if you get 0.3, that means that if you get A's, then you get added 0.3. So that becomes 4.3, giving you an A plus. Okay. So that's the whole thing. So each bonus point will give you a 0.1 additional score that you can add at the end of the semester when you are grading. So if you manage to answer like 20 questions, then that'll give you 2 answers, right? I mean, sorry, it'll give you 2 scores because 0.1 times 20 is like 2. So if you already got a good score in projects, then that is like overkill. Like that would be too much. So I'm hoping that diverse number of students will be able to answer questions. Like if one student hogs the question all the time, then that student will get like, I don't know, like 20 or 30 different questions right, and then get like 3 or 2 points in total, and then after all the projects, that guy will get like 6 points, which is too much because 4.3 is A plus. So please don't do that and give other people a chance. So does that answer your question? 목요일 프랙티스 세션은 TA분들이 진행하십니다. Sorry for the basic question, 박지훈님. So in n-fold cross-validation, if there are 3 data set like D1, D2, D3 in the first fold, you train. Anyway, by the way, you can leave. Actually, you don't even have to attend this class. You don't have to come because I'm recording this and then uploading on YouTube. So you can leave whenever you want. You don't even have to come. So please don't stick around for my sake. It's 12:05. So if you have to be somewhere, just go. TA가 진행하실 프랙티스 세션 보너스 포인트 있나요? 아마 없을 겁니다. 뭐 제가 딱히 TA 분들이 퀴즈를 꼭 내고 싶으신 게 아니면 딱히 없을 겁니다. Yep, the bonus point is made by answering my quiz. Yes, actually not quiz. It's a question. Going back to the Kwakjio's question. If there are 3 data sets like D1, D2, D3, and first of all, you train with D1, D2 and test with D3. Then before second fold, train with D1, D3 and test with D2 and then train firmware fine. 네, 무슨 뜻인지 잘 모르겠네요. 그냥 한국말로 물어봐 주시는 게 나을 것 같습니다. 아마 매 폴드마다 그 모델을 새로 학습하냐고 물어보시는 것 같은데 맞습니다. 매 폴드만 새로 학습하는 겁니다. 새로운 트레이닝 셋에 대해서 새로 학습하고 새로운 테스트 셋에 한 번 테스트하는 겁니다. 김정우님, 네, 그렇습니다. 오늘 제가 물어본 모든 질문들은 다 보너스 퀘스천에 보시면 됩니다. question from 한을수. L1, L2 놈이 슬로프를 영어로 설명하는 것 같은데 메모리 리가 없을까? L1, L2 놈이 슬로프를 영어로 수렴하게 하는 것 같다. 무슨 뜻인지 잘 모르겠네. L1, L2 놈이 슬로프를 영어로 수렴하게 한다. 무슨 슬로프? 그 로스 펑션의 그레디언트 얘기하시는 건가요? 무슨 뜻인지 질문이 잘 이해가 안 되네. 어, 여기다 잠깐 그림을 그려드리자면 여기 계신 분들 다 남아 계신 분들이니까 아까 아이고. Oh, actually, I should speak in English. So about L1 and L2 norm. So if you recall this two-dimensional function with concentric circles as the loss function. So this is your loss landscape. And if you use L2 norm, what you mean basically is that this is your L2 distance from the origin. What you mean is that, so if you recall L2 norm, it was 2 over lambda, 2 over lambda W squared, right? What you mean is that, so there's loss function here as well, plus loss. And you want to minimize both at the same time. So minimizing the loss means that you want to go down to this point, and which is actually the other way around if you think about this guy, because in order to minimize this, you want to go here to the origin. Because here is the value of norm is here is obviously this is larger than this and this and this, right? So in order to minimize this guy, you want to go here, but in order to minimize this guy, you need to go here. So how do we balance the two? That's the question. So that is where L2 norm comes in. So you want, while you're going here, you would still want to somehow minimize this. You don't want to go too far away from this guy. So there's like a power struggle between the two. That is L2 norm. L1 norm is a little bit different. L1 norm is, because L1 norm is based on the absolute values. Like this. So you still want to be here, which is the, oh, sorry, I should write down L1. L1 is like lambda sigma, like WIs plus lambda. I have some plus loss function, and you want to minimize both at the same time. And so you still want to go here because this is the point where this guy is at 0, right? But again, there's a power struggle, but you want to be here and here at the same time, and usually you'll end up in some place like this, or because your loss, your if you look at the loss function, loss landscape here, actually this is I've drawn this too nicely, but yeah, okay. With this depiction, I guess I can't really convey my point. But what I was trying to say is that because if this is the same, this concentric circle is where the loss value is the same, right? All these circles, all the lines in this circle have the same loss value. All this circle, all the points on this circle have the same loss value. All the points in this circle all have the same loss value, right? So, for example, with this kind of like very sharp edges like this, then it's likely that you will end up in this rather here, actually you will. So if you look at this guy, you'll end there's the likelihood of you ending up in here, like here, or rather here, or here is more likely to that you end up here in one of the axes. That is why if you will end up in one of the axes, then this guy is survives because it's here, but this guy dies out because it's 0 here. That is why your coefficients become sparse. So if your loss value, if you use an L2 norm, then it becomes a smooth loss function. So there is a very high likelihood that you will end up like here or here or here. But if you use this square function, like L1 function, then the likelihood is you will end up here or here or here or here or here or here. That is why it becomes sparse. So I hope that this kind of clarifies which regularization method you should use. Yeah, adding those two. I'm not sure how you would add those L1과 L2 놈을 같이 사용하는 방법도 있긴 한데 제가 그것까지는 뭐 공부를 한 지 하도 오래돼가지고 기억이 안 나는 그런 뭐 스트래티지들도 있습니다. 제가 아까 말씀드렸던 뭐 엘라스틱 넷이나 이런 것들은 뭐 그러니까 베리어블로 그룹핑을 해서 뭐 그룹 오브 베리어블에다가는 뭐 그러니까 그룹 차원에서는 L1을 쓰는데 뭐 각 차원에서 뭐 L2를 쓰고 그래가지고 뭐 일정 그룹을 막 꺼지게 한다거나 그러니까 스파르스 그룹을 만들고 싶다거나 뭐 이런 막 그런 것도 있는데 요즘은 그런 거 잘 안 씁니다. Question from Kwakjo is kind of blurry between supervised learning and reinforcement learning if you consider the input data as environment. 인풋 데이터가 environment가 아닌데 environment은 보통 이제 시뮬레이터를 얘기해요. 뭐 아타리 게임이나 아니면 뭐 이제 뭐 바둑판이나 이런 것들이 시뮬레이션이죠. 그래서 시뮬레이션을 해서 내가 아무 짓이나 했을 때 그 컨시퀀스, 리워드가 주어지는 거를 이제 우리가 environment라고 부릅니다. 그러니까 이제 내가 아무 짓이나 해도 리워드가 나오기 때문에 그 리워드를 보고 배우는 건데 슈퍼바이즈 러닝은 학습 데이터를 보고 배우는 겁니다. 그러니까 이제 이렇게 하면은 이게 나온다라는 걸 보고 배우는 거고 그게 슈퍼바이즈 러닝이고 reinforcement 러닝은 이렇게 하는 거를 아무도 가르쳐주지 않아요. 그냥 맨 땅에 던져놓고 자기가 알아서 하다가 여기저기 부딪혀 보면서 이제 점점 깨달아가지고 하는 게 이제 그 강화학습의 핵심 철학인데 물론 이제 아까 말씀드린 챗GPT 같은 경우는 그 철학이 이제 약간 흐려지죠. Question from 서희마 and for the cross validation에서 매번 from scratch 이거 평균 내는 게 아니라고 하셨는데 each for the solution performance 가지고 어떻게 더 나아지? 아니 그러니까 제가 아까 말씀드렸듯이 enforced cross validation 하는 거는 내 모델의 테스트 퍼포먼스를 안정적으로 추정하기 위해서 하는 거지 퍼포먼스를 올리려고 하는 게 아닙니다. 이게 한 번만 하면은 내가 이렇게 있을 때 여기 한 번에 대해서만 내가 테스트 퍼포먼스를 재면 그 테스트 셋이 뭐 운이 좋아서 쉬운 샘플로만 가득 차면은 성능이 좋게 나올 거잖아요. 그러면 나는 그거 한번 뭐 내 모델 성능 되게 좋네 그러고 생각을 할 거 아니에요. 근데 실제로 운이 좋았을 뿐이잖아요. 그렇기 때문에 여러 테스트 샘플에 대해서 테스트를 해보고 평균 성능을 얻어야지 내 모델의 진짜 테스트 퍼포먼스를 알 수가 있다는 겁니다. 퍼포먼스를 올리는 거하고는 아무 상관없어요. 선재상님, 밸리데이션 셋으로 모델 매번 평가하면 학습도 늦어지는데 혹시 밸리데이션 매번 평가할 필요 없이 보통 이제 뭐 100 이터레이션, 100 업데이트 한 번, 뭐 1000 업데이트 한 번, 1 에포기 한 번, 뭐 이런 식으로 이제 자기가 횟수를 정합니다. 이건 이제 적당하게 정하시면 됩니다. 뭐 그걸 이제 얼마나 자주 해야지 내가 시간을 아끼면서 모델의 성능을 가장 적절히 측정할 수 있냐라는 연구를 하시는 분도 계실 수 있겠죠. 근데 뭐 저는 뭐 딱히 본 적은 없습니다. 최동현님, is there any criteria or consideration for defining the loss function? Usually, actually, no. Loss function is pretty much fixed for the kind of test that you want to do. If you want to do in binary classification, 99% of the time you use cross entropy. If you want to do multi-classification, 99% of the time you use negative log likelihood. And same goes for other tests. But if you want to do regression, 99% of the time you use either mean absolute error or mean squared error. You can always, like design your own function, but still, like, there's very rarely the case that is required. Question from 이지희님, L1 놈과 L2 놈 같이 네, 답변 드렸던 것 같고요. Question from 서희마, 그럼 오버롤 좋은 밸리데이션이 나오면 오버롤 좋은 밸리데이션이 아니라 좋은 테스트 퍼포먼스가 나와야겠죠. 。 그러니까 이렇게 내가 이렇게 있을 때 5폴드를 한다고 치면은 5폴드를 한다고 치면은 여기서 한번 그러니까 이제 어, 여기서 학습하고 여기서 테스트 한번 하는 거 한 번. 그다음에 아까 얘기했듯이 여기서 학습하고 여기서 테스트하는 거 한 번, 또 여기서 테스트하는 거 한 번, 한 번, 한 번 할 때마다 5번의 총 테스트 결과가 나올 거잖아요. 그래서 처음에는 뭐 애큐러시가 95% 나오고 두 번째는 84% 나오고 그 다음에는 93% 나오고 92% 나오고 뭐 76% 나왔다. 이러면 이제 예를 들어서 그러니까 이제 예를 들어서 애큐러시가 뭐 말도 안 되지만 뭐 60%, 50%, 60% 아니 다시 60%뭐 20%, 80%, 30%, 95% 이렇게 나왔으면은 그냥 엄청 불안정한 거죠. 그러니까 이런 정도의 베리언스가 있으면은 내가 이게 그러니까 내가 이걸 함으로써 추정하는 건 테스트 퍼포먼스를 추정하는 거잖아요. 마치 내가 아까 얘기했듯이 남자들 다 모아놓고 키 재가지고 우리나라 성인 남성의 평균 키 추정하듯이 지금은 5번을 보고 내 모델 테스트 퍼포먼스를 추정하는 거라고. 그러니까 추정을 하는 거예요. 스태티스틱 에스티메이션 하는 건데 그때 아까 얘기했듯이 막 10, 50, 30, 90, 60 이렇게 나오면은 베리언스가 엄청 크잖아요. 그렇기 때문에 이건 마치 내가 키를 재는데 5명 불렀더니 한 명 130, 한 명 190, 한 명 220, 한 명은 뭐 150 이러면은 이거 평균 내봤자 의미가 없잖아요. 이거 평균 내봤자 애초에 베리언스가 너무 크기 때문에 이게 과연 안정적인 평균 추정이라고 할 수가 없는 것처럼 여기서도 10%, 50%, 90%, 30%, 70% 이렇게 나오면은 이렇게 해봤자 평균적으로 안정적인 테스트 퍼포먼스 추정이라고 볼 수가 없기 때문에 더 많이 테스트를 해야 됩니다. 더 많이. 근데 이제 그게 현실적으로 어렵긴 한데 하여튼 그런 식으로 사용할 수 있다는 거예요. 그래서 이게 예를 들어서 운 좋게 75, 74, 73, 74, 76 이렇게 나왔으면 굉장히 안정적이죠. 그러니까 이만큼만 해도 이미 베리언스가 되게 낮기 때문에 아주 안정적인 테스트 퍼포먼스를 추정했다라고 할 수 있는 거고요. 그런 식으로 사용하시면 됩니다. 최종원이 가우시안 믹스처 모델에서 각 디스트리뷰션의 웨이트 썸 할 때 웨이트도 따로 구하는 방법이 있나요? 네, 웨이트도 구하는 방법이 있죠. 웨이트까지 구해야 됩니다. 사실은. 그러니까 가우시안 믹스처에서 추정해야 되는 게 총, 그러니까 가우시안이 K개면은, 어, 2 곱, 2K, 2K 더하기 K겠구나. 네. 2K, 3K개를 구해야겠네, 3K. 그러니까 이제 각 K 민즈, 그러니까 이제 K 가우시안을 한다 그러면 각 가우시안마다 민과 베리언스, 그러니까 뮤하고 시그마 구하셔야 되고, 그럼 이제 벌써 2K잖아요. 그 다음에 각 가우시안의 배합을 구해야 되기 때문에 그것도 또 구해야 돼서 이제 총 3K개를 구해야 됩니다. 그걸 다 같이 추정하는 걸 이제 EM 알고리즘이라고 expectation maximization 알고리즘이라는 걸 이제 구하셔야 됩니다. 안수현님, 오버피팅과 정상 학습의 성능이나 로스를 구분하는 정량적인 기준은. 그러니까 오버피팅을 했다는 건 사실 테스트를 하기 전까지는 진짜로 알 수는 없습니다. 근데 테스트는 딱 한 번만 할 수 있잖아요. 그렇기 때문에 사실은 오버피팅을 하고 있다 안 하고 있다를 학습하는 중에 아는 건 불가능한데 그걸 간접적으로 아는 방법이 바로 이 밸리데이션 셋을 쓰는 겁니다. 그 데브 셋이라고 말한 거 있죠. 그걸 쓰는 겁니다. 그래서 이제 트레이닝 셋이 그러니까 이제 내가 데이터 셋이 이렇게 있을 때 이만큼 트레인, 이만큼 밸리데이션, 이만큼 테스트를 쓴다 그러면은 학습할 때 실제로 파라미터, 그러니까 코에피션트를 업데이트하는 데 쓰는 건 얘고 얘를 간간히 평가를 해보면서 평가할 때 이제 내가 학습을 하면 이게 이제 학습 횟수예요. 넘버 오브 이터레이션인데 넘버 이터레이션인데 트레이닝 로스는 점점점 떨어지겠죠. 이게 이제 트레이닝 로스인데 이벨 밸리데이션 로스는 어느 순간에 올라간다고 얘도 이렇게. 왜냐하면은 트레이닝에만 너무 오버피팅 되다 보면 심지어 밸리데이션에도 이제 미스 그 제너럴라이즈가 안 되는 시기가 오거든요. 그럼 이제 그때쯤부터 이제 끝내면은 그때 이제 딱 끝내는 거죠. 그러면 이제 호플리 밸리데이션 셋의 디스트리뷰션과 테스트 셋의 디스트리뷰션이 비슷하다 그러면은 비슷한 커브를 그릴 거잖아요. 비슷한 커브. 그러니까 내가 이제 밸리데이션 셋 기준으로 오버피팅 나기 전에 학습을 끊으면은 테스트 셋 때도 오버피팅이 안 날 거다라는 이제 추정을 할 수 있는 거죠. 도움이 되셨나요? 답변이 되셨나요? 네, 좋습니다. 네, 좋습니다. Right, is there any more question? So all the things that come after this class, we will never touch upon the basic ML anymore. It's all all deep learning and very advanced stuff. So if you haven't figured, if you can't follow the material today, I strongly suggest that you change. Well, actually now it's already changing the course is impossible. You should like consider dropping the course if you care about your grades actually. Right. So if you have any question at all, please post them on Classroom after the class, and I'll upload the recording of this video anyway. So you can recheck the video as well. All right. Thank you very much. 감사합니다.
감사합니다.
네, 감사합니다.